Let's start radii in multiple bonded atoms. In case of multiple bonded atoms, the radii are named as multiple bond radii. For example, the radii in ethylene and acetylene are named as double bonded and triple bonded radius respectively. Multiple bonds are shorter than the single bonds between the same pairs of atoms because of the additional bonding. Electrons pull the atom close together. Let's compare the length of various carbon-carbon bonds in table 2.2 along with nitrogen-nitrogen bonds. Here you can see that the number of bond increasing, the radii of an atom decreases. Hybridization and atomic radius. The atomic radius of an atom also depends upon the type of hybridization used by concerned atom. For example, the atomic radius of carbon is different in methane, ethene, and acetylene as shown in table 2.3. Ionic and crystal radii. The ionic radii refers to the radii of an ions in an ionic crystal. The ions formed by the loss or gain of an electron from the outermost shell or atoms. The ions formed by loss of electrons are known as cations, whereas ions formed by the gain of electron are known as anions. Metals usually form positive ions when an electron is removed from the atom to form the cation. The size shrinks, that is, decreases considerably. Thus, the radius of an cation is always smaller than that of a cation from which it is derived. For example, the radius of lithium is 1.52 angstrom, whereas the radius of Li positive ion is only 0.9 angstrom. This is because when an electron is removed from an atom, the attractive forces of the nucleus on the remaining electron increase. This results in the decrease in the size of an ion. In the above example, the loss of 2s electron from the lithium leaves the lithium ion, the Li plus with no electron in the n is equal to 2 shell. The decrease in size will be more in cases where 2 or more electrons are removed. For example, in case of aluminium 3 plus, the size reduces almost 50% of the neutral aluminium ion. The radius of aluminium is radius 143 picometer, whereas the radius of aluminium 3 positive ion is 68 picometer. The anions, on the other hand, are always larger than the atoms from which they are derived. Here, the explanation is just opposite to that. It is used in the form of cations. For example, the fluorine atom, which have the atomic number 9, have 9 protons and 9 electrons. On forming the anion, the nuclear charge is still plus 9, but there are 10 electrons in the anion. Thus, the fluoride anion is much larger than fluorine atom because of increased electron-electron repulsion. Determination of ionic radius. A number of methods are known to determine the ionic radii of the ions, but Pauling's method is the most widely accepted method. However, this method is limited to univalent isoelectronic ions. This method is based upon the observed internuclear separation in the four crystals, namely NaF, KCl, RBBr, and CSI. These compounds were selected by the Pauling because they have almost the same radiation ratio, that is 0.75, and nearly the same ionic character, and in each case the cation and anion are isoelectronic, means that they have the same number of electrons. Two basic assumptions are made by the Pauling while assigning the radii to the individual atoms. The cation and anions are assumed to be in contact. The radius of the ion inversely proportional to the effective nuclear charge of an ion, that is, the radius of an ion is 1 upon Z effective, whereas the Z effective is minus the effective nuclear charge from the screening constant. So we have get the formula. The radius of an ion is C upon Z minus S, where C is the proportionality constant, has the same value for two isoelectronic ions. Let's take a particular example of sodium fluoride to explain the concept of Pauling for evaluating the ionic radii. The internuclear distance in NaF has been experimentally determined by X-ray technique to be 2.31 angstrom. Thus, the radius of Na plus and Cl minus is 2.31 angstrom, the first assumption of Pauling. Now both Na plus and F minus ions are isoelectronic, that they have 10 electrons and consequently have the same screening constant. The effective nuclear charge on Na plus and F minus can be calculated by subtracting the screening constant from the actual nuclear charge. The effective nuclear charge on the Na plus is Zna minus screening constant, that is 6.5, and the effective nuclear charge on fluorine atom is Zf minus screening constant, that is 4.5. According to Pauling, the radius of Na plus and F minus ion can be evaluated from the equation second. So the radius of Na plus is C upon 6.5 and the radius of F minus is C upon 4.5. Substituting the value of 4 and 5 in equation third, we get the proportionality constant 6.41. Using the value of C in equation 4 and 5, we get the radius of Na plus is 0.95 angstrom and radius of fluorine is 1.36 angstrom. Now discuss about the size of anion and cations. The ions are formed by the loss or gain of electrons from the outermost shell of an atom. In case of cations, the size is invariably smaller than the parent atom. This is because with the removal of electron from the atom and magnitude of nuclear charge remain the same while the number of electron decreases. As a result, the nucleus exerts more attractive forces for the remaining electrons. In the other words, the nuclear charge per electron increases and the electrons are strongly pulled towards the nucleus. This results in the decrease in the size of the resulting ion. When more than one electron is lost from the atom, the effective nuclear charge increases substantially. This results further in the decrease of the size of the resulting ion. The ionic radii of alkali and alkaline earth metals are shown along the covalent radii in table 2.4. In case of anions, the size is larger than the parent atom. This is because with the gain of electron in the outermost shell, the total number of electron increases whereas the nuclear charge remains same. As a result, the same nuclear charge is now exerted upon the number of electrons. It means the effective nuclear charge per atom decreases and thereby the force of attraction between the nucleus and the electron decreases. This results in the increase in size. Periodic trends in ionic radii of isoelectronic atoms. Ions which contain the same number of electrons but differ in the number of protons in the nucleus are called isoelectronic ions. The effect of nuclear charge on the ionic size can be shown in the isoelectronic ions given below in table 2.6. Whereas the ionic radii decreases with the increase in the nuclear charge, the radii of isoelectronic ion decreases. This is because with increase in nuclear charge, the effective nuclear charge per electron increases and this results in the decrease of ionic radii in a period. Now discussing about the van der Waals radius. Before we discuss the van der Waals radius, it is important to distinguish between the intermolecular and intramolecular forces. Intramolecular forces are the forces that are responsible for the formation of a chemical bond, whereas intermolecular forces are weak attractive forces between the atoms and molecules. Intermolecular forces holds two or more atoms together and often are called van der Waals forces. For example, iodine is solid at a room temperature. The forces that hold the molecules together in the solid are known as van der Waals forces. The van der Waals radius is defined as the one half of the intermolecular distance between the adjacent atoms belonging to the two neighboring molecules of an element in a solid state. Therefore, it is half of the distance between the two bounded atoms of an adjacent molecules in the solid state. Van der Waals radius correspond to the closest approach of two atoms. So the radius of van der Waals is the intermolecular difference between the two non-bonded nearest neighboring atoms divided by 2. The van der Waals radius is a non-bonding type of radius for an atom with a closed configuration. Therefore, it is not surprising that the van der Waals radius of chlorine is essentially same as the ionic radius of chloride ion. The ionic radii of a non-metal generally be taken as reasonable values to be used as the van der Waals radii. This is because both possesses a complete octet of electron as shown.